In part two of rational functions, we're going to look at graphing rational functions. So just a reminder that we went over in the previous video how to find horizontal and vertical asymptotes. And so we're going to use that to figure out how we graph these rational functions. So here's a little synopsis of the process for graphing rational functions. First, you want to address any asymptotes. Determine if the function has vertical asymptotes and graph them as dashed lines. If the function has a horizontal asymptote, graph the asymptote as a dashed line as well. You're going to find any intercepts. Determine the x-intercepts by setting the numerator equal to 0 and solving for x. Determine the y-intercept by finding f of 0. This is the same process that we've used for all types of functions to find our y-intercept. Then you'll plot points. It'll tell you how many points in the program that you need to plot between each of the vertical asymptotes. It says, typically, your instructions will tell you to start by drawing the vertical and horizontal asymptotes, then plot the intercepts, if any, and plot at least 1 point on each side of the vertical asymptote. Then you'll be able to click on the Graph a Function button. So let's get started. For this example, first thing I'm going to do is I'm going to go ahead and factor the numerator and the denominator. I'm going to write it out as its factored form and see if anything cancels. When I factor this polynomial, both the polynomial in the numerator, I get x plus 5 times x minus 1. When I factor the polynomial in the denominator, I get x minus 6 times x plus 1. So nothing will cancel, meaning we don't get any holes in this polynomial. So the first thing I'm going to do is find my vertical asymptotes. So the first one, the way I do that is I set the denominator equal to 0. So that's going to be x minus 6 times x plus 1 equals 0. I have to set each of the factors of this equal to 0. So it's going to be x minus 6 equals 0 and x plus 1 equals 0. I'm going to add 6 to both sides for this one. So I get x equals 6 is my first vertical asymptote. I'm going to subtract 1 from both sides on this one, and I get x equals negative 1 as my vertical asymptote for this factor. So I'm going to go ahead and graph those with a gray dotted line. So remember, those are our vertical asymptotes, which are vertical straight lines. We graph them with a dotted line. Same thing with the 6. There we go. So those are our two vertical asymptotes. To determine if a function has a horizontal asymptote, we look at the degrees of the numerator and the denominator. So the degree of the numerator is 2, and that's for the numerator. The degree of the denominator is also 2. So when they have the same degree, then the horizontal asymptote is equal to the leading coefficient from the numerator over the leading coefficient of the denominator. So that's going to be 1 over 1, which just equals 1. So I'm going to draw a dashed line at y equals 1. It's the horizontal line that goes through 1 on the y-axis. And it goes forever in both directions. Same thing with these vertical asymptotes. I can move this up, actually, because this is going to go down, 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 down. Here we go. All right. So then we want to find the x-intercepts and the y-intercept if they exist. So let's start by finding the x-intercepts. We take the numerator and we set the numerator equal to 0 and solve for x. So my numerator was x plus 5 times x minus 1. So this is how we find x-intercepts. Okay, so I'm going to take each of those factors and set them equal to 0. X plus 5 equals 0. We get the x-intercept, x equals negative 5. So I'm going to plot that in green right here. Then I have x minus 1 equals 0. Add 1 to both sides, so I get x equals positive 1. These are my x-intercepts. So here we go. We have two x-intercepts. Then we're going to find our y-intercept by finding f of 0. This is how we find the y-intercept. We find f of 0. Now I can just put this into the original, not the factored form. So we have x squared plus 4x minus 5. So that's going to be 0 squared plus 4 times 0 minus 5 over 0 squared minus 5 times 0 minus 6. So I end up getting negative 5 over negative 6 because 0 squared is 0, 4 times 0 is 0, so 0 minus 5 is negative 5, and 0 squared is 0, minus is 5 times 0, which is 0, 0 minus 6 is negative 6. The negative divided by a negative is equal to a positive, so that equals 5/6. So I'm going to come on my y-axis and I'm going to plot 5/6. Now, if you get one that has a nice little fraction like that, you're going to use that plot pointer, the point plotter, funny, okay, the point plotter tool in the program to be able to accurately plot that point. So that point would be 0, 5, 6, and you would just use the plot a point tool to plot that exact point. So to find additional points, I have one on this side right now. I'm going to plot, or I'm going to find, I'm not going to put it right like that because that's confusing. I have the x-intercept right here. And so I'm going to find f of negative 2 to find another point. That's just following the same process. I'm going to find f of negative 2. I have 2 points in this middle range, so it's very likely that this is going to look like here. Now notice you can cross over a horizontal asymptote, but you cannot cross over a vertical asymptote. Okay. Oftentimes horizontal asymptotes help us determine in behavior of a function, and so they give us some guidelines on that. You'll be able to see that here when we graph this last part, because it's going to look something like this. But remember, in the program, it might only require you to do 1 point on each side of the asymptotes in addition to the intercepts. But I'm going to go ahead and find f of negative 2. I'm going to find f of 7 and f of 8. I'm going to pause and write out that work, and then you can check your answers so we can find these points and have enough information to graph this rational function. So I found f of negative 2 with this work right here, and you end up getting negative 1 1/8, or negative 9/8, which is about right here. So I did a pretty close job with graphing that. Let's do f of 7. So for f of 7, we end up getting the point 7, 9. So I'm going to go ahead and plot that here, 7, 9. And then we're going to do the same thing for f of 8. Calculate f of 8, we end up getting 5.0556. It's a fraction number, but you can use your calculator to get a decimal approximation. So 5, just a little bit more than 5. So that point's going to be right here. And so we can see that this trends down like this, and then would go along that horizontal asymptote. Now remember, you have a tool in the program that we use to actually graph it once you get a certain number of points. So it's not going to be that nitty-gritty with you needing to be able to graph it by hand, but it's good to practice by hand first so you actually understand the process and the tool that's being used. If you need additional points, you can find additional points. You can find f of 10 and find out where that is. You can find f of 4 to make sure you know exactly where this point is supposed to go. But the more points you have, the more accurate your graph is going to look like. But again, just follow the instructions from the topic. Okay, on this next example, we have graph f of x equals 2x squared over x squared minus 4. So we first want to find our vertical asymptotes. So we take our denominator. So to find vertical asymptotes, we're going to take our denominator, which is x squared minus 4, equals 0. Then we're going to solve for x, so we get x squared equals positive 4. Then we take the square root of both sides, but remember when you do that, you get plus or minus 4. So we get x equals, plus or minus the square root of 4. So that's going to give us plus or minus 2. So we have two vertical asymptotes. We have a vertical asymptote, which I'm going to do in red at x equals negative 2. And we have a vertical asymptote at x equals positive 2. So remember to plot those lines or draw those lines with a dashed or dotted line. The system will allow you to select that option to make a dotted line on your graph. Then you're going to go ahead and find any horizontal asymptotes. Let's do that in a different color. So let's do that in blue. So a horizontal asymptote occurs based on the degree of the polynomial. The degree of the polynomial is the top or the numerator versus the degree of the polynomial in the denominator. And so we look at the degrees. The degree here is 2. The degree in the denominator is also 2. So that means that we have a horizontal asymptote at y equals the leading coefficient of the numerator over the leading coefficient of the denominator, which equals 2. So at y equals 2, we have a horizontal asymptote. Now remember, you can cross over a horizontal asymptote, but you cannot cross over a vertical asymptote. So it's going to be super important that we find good points on this one. And the next step we're going to do is we're going to find our x-intercepts. Our x-intercepts occur where the numerator of the function equals 0. So we have x-intercepts. We're going to take our numerator, which is 2x squared, and set that equal to 0. Divide by 2, x squared equals 0, so x equals 0. So our x-intercept is at x equals 0. So that is also the origin, because where x equals 0 on the x-axis is also where y equals 0 on the y-axis. So we have that x-intercept. For our y-intercept, we're going to find f of 0. So that's going to be f of 0 equals 2 times 0 squared over 0 squared minus 4, which equals 0 over 4, which is negative 4, which is 0. So we have already plotted that because that's the same as what our x-intercept was. So this is kind of a special case and a special polynomial, which means we probably need to find a lot of points to figure out what's actually going on with this polynomial. So remember, follow the instructions from the program that we're using to find the additional points that are needed, but the more you find, the better. So what I'm going to do is I'm going to recommend for this case to find additional points. I'm going to recommend doing f of negative 8, f of negative 3. So I get 2 points in this section. I'm going to suggest doing f of negative 1, f of positive 1, and then I'm going to recommend doing f of 3 and f of 8, because that'll give us 2 in this section. I'm just going to go ahead and have you solve those and then check your answers with this list after you come back. So go ahead and pause for a moment and then come and check your answers here. All right, so evaluating the function at each of these values gives us these. F of negative 8 equals 2.13 repeating. F of negative 3 was 3.6. F of negative 1 is negative 2/3. F of positive 1 is negative 2/3. And you'll see that there is now a nice symmetry to this. F of 3 is 3.6 and F of 8 is 2.3 repeating. So I'm going to go ahead and plot those. At negative 1 and at positive 1, x equals negative 1 and x equals positive 1, we have those negative 2/3. For x equals negative 8, we have 2 and a little bit of change. I'm going to plot that in green. At x equals negative 3, we get 3.6. So that's up here. 3.6 is like 3, a little bit more than 3.5. And then we have the same thing over here and over here. So if I were to draw this graph and use the grapher in our program, it's going to look like this in gray. Here it looks like a maximum, and then I'm going to come downwards to hit through here. It follows along our asymptotes. And then here we go. That is our graph for this function. The last part of our rational functions section is looking at slant asymptotes. Now, slant asymptotes only occur in certain specific situations. A slant asymptote only occurs if the degree of the numerator is exactly 1 greater than the degree of the denominator. To find an equation of a slant asymptote, divide the numerator of the function by the denominator using synthetic division, and then the slant asymptote will be of the form y equals the quotient. So to find the slant asymptote of this function here, f of x equals x squared plus 5x minus 5 over x plus 1, it has a slant asymptote because the degree of the top is equal to 2 and the degree of the bottom is equal to 1. And so this would have a slant asymptote. So what we're going to do is, remember, we're dividing by x minus c, but in this case our c is a plus 1, and so that would be the same as x minus negative 1. So our c that we're dividing by is negative 1. So we take negative 1, and we're going to divide into our numerator. So our coefficients are 1, 5, negative 5. We're going to do synthetic division on this. So we end up getting y equals x plus 4 is my slant asymptote. So if you're asked to find the asymptote of a rational function where the degree is 1 greater than the denominator, then you would need to use the synthetic division to find the line of the slant asymptote. If you are then asked to graph the slant asymptote, you can make a XY table, or you could plot the y-intercept and then use the slope to find another point and then connect those 2 points, which is something that we saw much earlier in the semester, and you can go back and review. So, all right. That should be the general gist of what you need to know how to do. The only other thing that you really need to know how to do is then determine the domain and the range of a rational function. But we know how to find the domain and the range. Essentially, the domain is going to be all real numbers minus any place where there's an asymptote, a vertical asymptote. And then our range will be all real numbers that the graph goes through. So if there's a horizontal asymptote or if there's a maximum value or a minimum value, you would write your range based on that information. So for example, we can go back and look at this one. The domain on this one goes from negative infinity to negative 2. And it doesn't touch negative 2 because that's a vertical asymptote, unioned with negative 2 to positive 2. I wrote infinity to positive 2 because it's these x values in between here without touching that vertical asymptote, unioned with 2 to positive infinity because we have all of these x values. Doesn't ever touch x equals 2. So that's how we write our domain. Our range on this one, let's find another color. Let's do purple. The range, it goes starting from negative infinity. It goes negative infinity to 0. And then it stops. It jumps up to approaching this line right here. So it goes from 2 upwards to infinity. So from 2 to infinity. So if they ask you the domain and range of the function, we know how to do that. We've done that several times. All right. Thank you so much. Bye.